one question about linearly independent sets that turns out to be pretty important is just how big linearly independent sets can be and still fit inside of some vector space, some subspace. So let's suppose that we have the span of some vectors, the v's here, and let's ask how many linearly independent vectors will fit inside of the span of the v's. So let's suppose that we have a linearly independent collection of vectors, which we'll call u's, and each one of these u's is inside the span of the v's, and all the u's are linearly independent. So what we're going to ask is just how many vectors can there be in this collection of linearly independent vectors? So really what we're asking is, what are the relative sizes of R and S? Right? Well, to get a handle on this, let's just write down everything that we know. So these u's, these u vectors, they're linearly independent, and that means that if we put them all into a matrix like this, along with some variables, a variable vector like this, and there must be R entries in this variable vector, and set it equal to 0, then this equation has only the trivial solution. Right. This isn't the definition of linear independence, but this is how we always check if a collection of vectors is linearly independent. So notice that one thing we can do is actually call this vector, give this matrix a name, the matrix whose columns are the u's. Let's call it capital U. And then what we have is that u times, in fact, this vector of the x, variables x, we could call capital X. Then we have the equation ux equals 0, and this has only the trivial solution. So this equation has only the trivial solution because the u's are linearly independent. Also, the u's, each of them individually are in the span of the v's. So what would that look like? Well, so we have all these u's, u sub I. Right? I is going to range from 1 to r because there are lots of different u's, and they're all vectors here. They're all linear combinations of the v's. So that means that each one of these is a sum from 1 to s, right? All of the v vectors show up, and they all have coefficients. Sorry, that shouldn't be an s, that should be a, oh, I erased too much. That should be a j. And so there are these coefficients. And the coefficient depends not just on what v vector you're on, but also it depends on which u vector you're trying to express as a linear combination of the v's, right? So each different u vector will have different coefficients for all of the v's. So this a should have a subscript for j, but also a subscript for I, like this. Now, it looks as if I've arbitrarily chosen which index goes where, but actually it isn't arbitrary at all. J is acting like a column index because, right, what we can do with a bunch of column vectors is put them all into a matrix as columns. In fact, we will, and we'll call this matrix V. And in this case, the subscript on the V vectors is acting like a column index, right? It tells you what column number you're on in this matrix V. So this J is a column index. And for this product, right, it kind of looks like it's trying to be matrix multiplication. But for it to actually be matrix multiplication, if we're summing over J, then if J shows up in the column position here, which it is, it's a column index, it should show up as a row index here. So that's why it shows up first, because the row index is first. Also, I over here is acting like a column index because it tells you what column of U you're on. So it should be a column index for the second factor in our matrix product. So I is a column index here. So this choice of putting the J first is actually not arbitrary. Because of the way I have this set up, we can actually summarize, right, this is actually, this equation is actually R different equations. There's an equation for I equals 1, there's an equation for I equals 2, there's an equation all the way down to I equals R. And if we put all of these into a matrix, right, we get U1 down to UR. That's the sum of Vj aj1 down to, right, U sub r is the sum of Vj ajr. But this is exactly the matrix V times, right, we have all these columns of A's, so the first column of all the A's down to the rth column of all the A's, but we can just call this matrix A. So what we've done is we've expressed our matrix U, which is this one, as V times A, and V is this matrix, and A is just some matrix of coefficients, right? All of these coefficients A are just the coefficients that you need to express all the U's as linear combinations of all the V's. So in fact, U breaks down as this product. U is, right, all of these vectors are in Rn, all the U's and the V's, so U has to have n rows, and there are r different columns in this big U matrix, so U is n by r. V also has to have n rows because the V's have n entries, so n. And there are s columns in this matrix, so n by s. So that means that A, on the one hand, it has to have s rows for this matrix product to be defined. On the other hand, because the result of this matrix product has r columns, A has to have r columns as well. Okay. So when we ask what's the relative size of R and S, look, we're really asking what is the relative size of, or what is the number of columns of A versus the number of rows of A, right? So let's think a little bit about the matrix A. Let's suppose that AX equals 0 has a non-trivial solution. Okay, in that case, so maybe we could call this the non-trivial solution. It's a vector. We could call it, I don't know what to call it. Can't call it U, can't call it V. Let's call it W. So W is a non-trivial solution, so that means W itself isn't 0, but A times W is equal to 0. But if we multiply on the left, on both sides of this by V, we get VAW equals 0. Okay, but V times A is U, right? That's what we have over here. So then we have U times W equals 0, and W isn't 0. But that's a contradiction, because look, U times X equals 0 can only have the trivial solution because the U's are linearly independent. So this is actually a contradiction. It's impossible that this happens. So the assumption we made was that A times X has a non-trivial solution. So that means that this assumption was wrong. A times X equals 0 must have only the trivial solution. So this has only the trivial solution. But that tells us something about the size of the matrix A. So remember that something we proved a long time ago is if a matrix has more columns than rows, then this equation has a free variable, right? In which case there are non-trivial solutions. So non-trivial solutions. But we just showed that this equation doesn't have any non-trivial solutions. It has only the trivial solution. But that means that R can't be bigger than S. So S has to be bigger than or equal to r, right? Remember, S was the number of V's, and R was the number of U's. Now this is a surprisingly important result. So this is telling us how many linearly independent vectors will fit inside of a span, right? If you have some span, the number of linearly independent vectors that fit inside of there, it can't be any bigger than the number of vectors you started with. This is actually a theorem called the Exchange Theorem. So if you have r linearly independent vectors in Rn, and each of those vectors is in the span of v1 through vs, then r has to be less than or equal to s. One reason, in fact the main reason, why this theorem is so important is because it lets us think about how many vectors can be in a basis. So suppose we have a subspace V with two different bases like this. Okay? So both of these, since these are bases, they're both linearly independent. That's just part of the definition of being a basis. But they're both bases for the subspace V. So that means the span of all of the U's has to be V, because the U's are a basis for V. But on the other hand, the V's are a basis for V, so that means capital V has to be the span of V1 through Vs. I've stopped writing all of my vector symbols. Sorry about that. Okay, but according to the exchange theorem, right, we have r independent vectors fitting inside the span of s vectors. That means that r has to be less than or equal to s. But also by the exchange theorem, we have s linearly independent vectors fitting inside the span of r vectors. So that means r has to be greater than or equal to s. Well, the only possible way to resolve this is that r is actually equal to s. And that tells us that these two bases have the same size. This sort of seems intuitive if you think about small dimensional examples. So for example, if we have a plane sitting in 3 space, right, we could span this plane with these two vectors, or we could span it with, say, these two vectors, and both of these vectors have two. Both of these collections, both of these bases have two vectors in them. But, you know, our intuition for small dimensional examples doesn't really tell us very much about very high dimensional examples. This proof that we just worked out works for any number of, any size of subspace V sitting in any size Euclidean space. So this is a very general fact. Any two bases for the same subspace have to be the same size. For that reason, we can actually make a definition. So given any subspace V inside of Rn, the numbers of the number of vectors in a basis of V is called the dimension of V. And this is well defined because we just proved that no matter which basis you choose, it will always have the same number of vectors in it as any other basis. And also we've proved that every subspace has a basis. So any basis will have the same number of vectors as any other basis, and so we call that number the dimension of V. Just to get a handle on this, let's look at two quick examples. So what is the dimension of Rn? Well, Rn is, we have a nice easy way to express Rn as the span of some linearly independent vectors. So there's the vector with a 1 in the first spot and a 0 everywhere else. And then there's the vector with a 1 just in the second spot and a 0 everywhere else. And so on, all the way down to the vector with a 0 everywhere except in the last spot. These vectors clearly span Rn because various linear combinations will let you put any number in any entry. But also, these are linearly independent because if you put these all into a matrix and then row reduce the matrix, well, when you put them all into the matrix as columns, you just get the identity matrix. So it's already row reduced, and it's already the identities, so it's linear. These are linearly independent. So these vectors span Rn, and they're linearly independent, so these vectors are a basis for Rn. This is actually called the standard basis for Rn. And how many vectors are there? Well, there's one vector for every place you can put a 1, and there are n different entries. So there are n vectors in this basis. And so that means the dimension of Rn is n. And that's good. If I asked you what the dimension of Rn was, you probably would say n. So it's a good thing that our definition of dimension is matching what you'd like to say about dimension. Okay, well, what's the dimension of the vector space that is only the 0 vector? So what's the dimension of this vector space? It's a pretty boring vector space. So what we're really asking is, how many vectors do you need to span this vector space? Not spam, span. So how many vectors do we have to put in here for this span to be just the 0 vector? Well, remember, we can only, whatever list of vectors we put here has to be linearly independent. If we put a non-zero vector in here, the span isn't going to be just the 0 vector. So really, the only vector we could possibly put in here is the 0 vector. But the 0 vector isn't linearly independent, right? The 0 vector, taken as a matrix, has a non-trivial solution to this equation. Right? In fact, you could choose any scalar x, and you'd have any non-zero scalar x, and you'd have a non-trivial solution to this equation. So we can't put the 0 vector in here either. So we can't put any vectors in here. But on the other hand, what is the span of no vectors at all? Well, if you take no vectors at all and multiply them by constants and add them up, you get the 0 vector. So the span of no vectors is just the 0 vector. And no vectors are linearly independent because if you have a matrix with no columns, there's no solution to this equation except the trivial solution. So this empty set of vectors spans this vector space and is also trivially linearly independent. So this basis with no vectors in it is the basis for this subspace. And that means that the dimension of just the 0 vector is the number of vectors in this basis, but that's 0. All right, so we find that the dimension of this subspace is 0. And this also makes sense because, right, if we were to plot this vector space, it would be just a point. And if I asked you what's the dimension of a point, you would say, well, it's 0-dimensional, right? A line is 1-dimensional, a plane is 2-dimensional, a point is 0-dimensional. And that's what we got. So you can see this definition of dimension is sort of matching up with our intuition, which is always a good sign.